of course, as other folks come in, they could just join us in session. All right, so welcome, folks. I'm Robert Sears. I'm the government chair for the ACT-IAC. That's the American Council for Technology Industry Advisory Council, Network and Telecommunications Community of Interest. I'm also the director of the NWAVE program within the National Oceanic and Atmospheric Administration, and I also wear the hat of the Federal IPv6 Task Force Chair. So you'll always see me and hear me pushing federal government moving towards V6. But today we're talking about the projects and activities that are going on in the NNT. So first I'll jump into the NNT, Network and Telecom Community of Interest, give you a little bit more background about us, what we've been doing for those who are maybe new. So our group here is to provide clear, impartial feedback and recommendations on network and telecommunication issues identified in collaboration with government and project sponsors and advisors. Really, that means we're here to help bind government and industry to offer the best advice, guidance, highlight what's going on in the world of networking and telecommunications for the betterment of the federal government. This is our leadership, myself, Richard Zelkowitz, who has retired from MITRE, but is now an independent consultant. Stephen Brand, he's our government vice chair from Department of Energy. Stephen Mathern, vice chair from AT&T. We have Deidre Murray from Deidre Murray and Associates, who's our programs co-chair. Lee Mosier from Fortinet, program co-chair also, and Ginger Crawford, our communications chair from GDIT. So we have a great group of folks. We also have a lot of government advisors. So government and industry are always welcome to join us at our meetings and provide content, ideas, whatever it may be, to help continue to push forward the great work that we're trying to do here. So over the past year, we're closing out the last year and we're into the new year. Usually starts around July, August timeframe. So these are some of the activities that we have going on. So we had in August, the Wizardry of NAS that Stephen Brand had helped put together and lead. This was a Understanding Network as a Service. That was a really great panel that we had with multiple industry and government entities. We're going to actually touch on that a little bit today in our overview of the project that we just completed on the operational use of non-terrestrial network technology. So that's going to be the crux of our discussion here a little bit later. And then we'll have a second part of that project that's going to be a panel discussion here on November 7th. We have GHS and Spectrum program coming up December 11th. And then we have a DoD 5G discussion topic that is coming up in January. We're going to pinpoint that date here soon, but keep your eye out there and join our mailing list, and that's to make sure you have the most up-to-date information on what the NNT is doing. So as I said, the operational use of non-terrestrial network technology, there's a paper that is now out and published. I'm going to talk about that here in a second. That was a project we completed this calendar year, really closed it out in September. Ongoing is the retirement and replacement for legacy copper networks. So that is still in progress. There's also a next generation network infrastructure task force that's going on in collaboration with the ACT-IAC acquisition community of interest, and that's still in progress. That's ongoing. That is looking at the acquisition side of telecom, things working with GSA for like EIS. So it's a great meshing of the two COIs. And then we got two new projects we're working on this year, modernizing federal networks from the campus and beyond. That's really taking the non-terrestrial and the retirement legacy copper networks, taking all that into account and where you can go forward in modernizing. So we say from campus and beyond because there's infrastructure at campuses, we got fiber plants, we have old copper plants, and how you modernize those, connect all the way up to the cloud, and what are those technologies allow you to do that. So that's what we'll be working on over this next year. And then we have a really good new approach on a project called the Foundation of Connecting Government and People. And this is really humanizing networking. A lot of we take it for granted. We have it on our phones. We're always connected to the internet. Things happen, and we don't understand the critical underpinnings of the network infrastructure. So we're really looking to kind of bind that through telling of various projects or going ons within either federal funding that are going into projects where we're solving problems. There's things happening in rural areas with broadband initiatives. But we want to try to humanize that through a project. So that's going to be very exciting to tell those stories and continue to show what's happening in the background of all this technology that makes us do our jobs and run the world every day. So what we're going to highlight here is the operational use of non-terrestrial networking technology. Again, we just published this paper. I'm not going to deep dive into this because I want to just give the highlights, but really what we looked at was, can the federal government leverage non-terrestrial networks for their day-to-day operations or even critical operations? So this is looking at things like LEO satellite, 5G, microwave. Yes, we know that there's a terrestrial point at some point, but in the immediate area, the RF spectrum that you may pick up to do your transport, is that feasible for day-to-day federal operations? So we took into different scenarios into account. What is the requirement for this? Is there a need because there's a site that's remote? Is the site doesn't have access to things like fiber or traditional Ethernet type services, or maybe it's too costly for the balance of the operation. Maybe it's a small site like 5-man, 10-man site, or maybe it's a sensor network and it's not feasible to put out a regular terrestrial network. And then mobility as well. Is there a mobile option that maybe the utility or the purpose is not always in the same location? So we took these things into consideration, and we did a survey across these different questions that we put out to the various agencies that wanted to participate. So they all had the same question base. And again, I won't go over that because we have a link that Renata put in to take you to this paper. And we ended up with 5 case studies. So we had 3 within NOAA, Department of Energy, and the Yukon-Kuskokwim Delta Tribal Broadband Consortium. So we had a tribal entity that participated to tell their story about their use of the technology that was of their choice, the non-terrestrial technology. This was the breakdown of those 5 projects. So you could see, use of cellular, private cellular, so that's a big thing, private 4G, 5G, and of course LEO being a very big hot topic right now just because of the reachability and bandwidth. The first use case was up in Alaska. This was with one of our unmanned radiosonde launch systems. There's the Starlink terminal. Radiosondes get launched from this little utility over here, this little hut that goes up. Telemetry comes back to the pad, and then we leverage the Starlink connectivity to get back to our N-Wave network. So again, I'm not going to deep dive into all these because I want you to read the paper where we have more details about each one of these. The air observation system, this is systems that are out every airport in the United States. These are over 900 locations. This actually is cooperation in many cases between FAA, NOAA, and the Department of Defense. But these systems have all been modernized utilizing 5G, so you could read about that. Our fleet, the NOAA fleet, leveraging Starlink as their comms over what used to be a traditional VSAT. So going from 1 megabit up to 100 megabits of download. It's a game changer for the fleet as we look at this case of mobility. You can read about that. Department of Energy, their Energy Science Network for field science, having sensor networks out in the middle of the forest and utilizing private 5G to interconnect sensors that are scattered all over a mountain range, then a Starlink terminal to get that back to their network. So again, another really great example of utilizing non-terrestrial networks there. And then in the case of the YKD, the Yukon-Kuskokwim Delta Tribal Consortium, to talk about their project that they did with using a combination of OneWeb and microwave to homes to connect their local community of, I think it was over 300 residents. So another great example. Please read the paper. It covers these other areas about cost consideration, types of emerging technology. The links there, Renata also put in the link. And at this time, I'm going to introduce Andrew Lee, who's a senior network architect with our program, the NWAVE program, and also a senior network engineer. What we're going to be talking about is two of the projects that the NNT has covered. Well, at least we had a program on network as a service. We have the non-terrestrial network project that I just talked about. And this particular project within our program covers both of those. So NWAVE has developed a software-defined network as a service for wide area communications for mobile use. So this was a proof of concept that we've also developed around a very specific technology to build a SD-WAN service that we could offer into customers that need mobility or they're in a hard to reach location. And so we're covering both those topics into this one very technical deep dive. So those of our geeky folks on the line here, you should enjoy this because this does go deeper into the architecture and how it is used. So I will turn this over to Andrew and let you take it away. Thank you.
Thanks, Rob. Again, my name's Andrew Lee. I'm a network architect on the NWAVE transport team. So my job is essentially, how do we get all of the NWAVE services that we offer to all the sites that need them. And I need to. So I'll talk about SD-WAN in general, and how we have implemented it as a transport service. I'll talk about a program called IMET and what our use case is, both with SD-WAN and the non-terrestrial network aspect. And then I'll talk about the field demo that I did, and what the results of that were. So SD-WAN in general, for those of you who aren't familiar, well, actually, let me take a step back first. Normally, when NWAVE is going to provide services to a site, like a river forecast center, for example, or the National Hurricane Center, we'll go to the site. We'll order some sort of telco level service, like from Zayo or whoever. So a couple circuits will come in with a couple beefy routers, Juniper MX type routers, or that kind of class of router. We'll have an out-of-band device, so in case we have to access the site when there's a failure. We'll have a performance measurement device. So there's a big stack of equipment. But like Rob said, there are cases where this isn't feasible or logical. Either the site's very small, or you can't get a reasonably priced telco circuit, or like with MAO, you can't have a cable out to a ship in the ocean. So if we have the capability to provide those services, but we can't get that circuit to provide that direct connection, that secure connection, maybe we can use SD-WAN to bridge that gap. So in addition to that, those cases where of unfeasibility, we also have situations that might be transient, or even an emergency situation. One of the kind of the background occurrences that happened, we have a site in northern Alaska that was isolated because of a submarine fiber cut, and at the time we didn't have a way really to get them back on quickly with, say, LEO. Also at the time, that latitude wasn't well served by Starlink anyway, so that was kind of a challenge in itself. But we can develop a service where we can provide something in an unexpected situation. And then we have since we're a federal agency, we have, security considerations, we have policy considerations. Um, the Rob kind of skipped over it, but like with the OMIO use case, we have these trusted internet connection uh, access points, TICAPs. So we have to provide uh, secure internet to our customers in a regulated manner, in a prescribed manner. Um, SD-WAN as an idea, though, it basically is you're building a virtual network topology over on top of something else. So the keywords that will come up are overlay, which is like that virtual network that you're building, and then underlay is whatever it is you have available to you to build that across. There's some sort of separate controller that will take all of your security policies, your service intent, um, whatever it is that you need to, from like a business perspective, what you need to consider, and distill that down into um, a router configuration. Um, so you say, I want to have a service here and provide it to this user, and then the controller will say, okay, I will build that for you. And then you have um, that like those access controls, this user can get to this service, but not that service. So that's kind of like the two sides of the coin for SD-WAN. So the security side, but also the transport side. So traditional or the 95% of vendors will say, well, I'll build an IPsec tunnel across my underlay network. I'll throw in some QoS, and that will provide my transport. So it's kind of the typical way. When N-Wave, when we were looking at what we needed specifically, we decided we would go with the Juniper SSR product line for a few reasons. Vendor selection can be tricky, and there's always, pros and cons. But this is what we picked. We decided to do a relatively traditional hub and spoke network where we basically have an SD-WAN aggregation layer that's adjacent to our regular network core. And again, going back to these trusted internet connection points, we decided to deploy this aggregation layer at those locations, and I'll get into why later. So that with their product, their controller, they call it a conductor. They have a conductor we can deploy on premise, so we don't have to worry about FedRAMP concerns because we can run the conductor in-house. But they also have support for their product in Mist, for those of you who use Mist. One of the differentiators for the SSR line, and it dovetails with one of our requirements, we're gonna make, I guess I could call it an assumption. We're gonna make an assumption that when we're gonna deploy the service, we're gonna deploy it in a bandwidth constrained environment. Starlink, for example, you can get, 250 meg across, and that in some use cases can be considered bandwidth constrained. Or, there'd be use cases where that bandwidth is limited by other factors. So one of the differentiators for Juniper is what they call secure vector routing. And I'll kind of dive into this a lot more later, but they call it tunnelless. It kind of is, but I'll talk about it again later. So they use SVR rather than IPsec tunnels. They also have a technology called adaptive encryption. So they'll look at the payload of a packet and they'll say, well, this is already a TLS packet. This is already an SSH packet. It's already encrypted. So I don't need to spend the computation and the bandwidth to encrypt it again. That's that level, or at least for this particular application, we can decide that level is redundant. So we can save both time and bandwidth by just letting that packet remain in its already secure state. We can offer both layer 3 IP services as well as layer 2 services analogous to EVPN or VPLS or something. One of the more important things is we can have a granular idea of the health of our overlay. We can monitor how well the network is performing, get a really good idea of what the user experience is, and then maybe even make routing decisions based on that. There's hardware high availability for if you need additional redundancy at a site. You can set down 2 physical routers, and they will as one device. If one were to fail for whatever reason, the user is not going to notice. The state is maintained in both devices, and it would just switch to the backup. This is what the actual hardware looks like in. So at the core side, we have the Juniper 1300 SSR 1300 device, rack-mounted 1RU. At the sites, we selected the SSR 300 for a few reasons. It has 8 client ports, 6 of which are RJ45 GigE, and then 2 can be SFP. It has a built-in LTE radio, but it's also a compact device. There's no fan, so the power requirement is very low. So we're talking like 40 watts or something. So and I'll touch on this again later. In a situation where you don't have commercial electric, having low power draw is important. So this is what kind of the high level of the topology, and SSR 130 at a site would establish peerings with each of the aggregation routers. So we have 4 deployed right now on our network. 2 are in the Denver area near our Denver TICAP, and 2 are in the DC area near our DC TICAP. So the remote sites will form peerings with each. Each of the peerings we can monitor those for performance. And if one of these goes down for whatever reason, we can shift that service to a different peering. So a little more on telemetry. When 2 routers on the network establish that peering, one of the things it will do is it will send occasional bursts of BFD packets. BFD is bidirectional forwarding detection. So it's a well-known way to make sure a connection is actually passing traffic. We use it for protocol redundancy. So you want to make sure that yes, you can send a packet out, but is it do we have packets flowing in both directions? How much packet loss is there, etc. And then we can also do inline monitoring. So we do these BFD probes every once in a while, but we can also say, oh, I just sent you 10,000 packets of user data. How many did you get? And the other side said, the other side says, oh, I got, 9,995. So we know we dropped 5 packets, even though we're outside of one of our, active measurement timeframes. So there's a lot of ways we can get an idea of the health of any portion of our network. And then we can make decisions on that. So we take loss latency and jittering into consideration. And then we can kind of compile that into a meta idea called a mean opinion score. So if you want to be more nuanced and say, and you can do this, you can say, well, if packet loss exceeds 5%, I don't want to use this path anymore. Or you can say, if a link is bad for some definition of bad, taking into consideration loss latency and jitter, then we can use our mean opinion score. And so we can say, I'm going to disqualify this link now or this peering now, because that we consider that bad for whatever definition of bad that we want to have. So all this is sent back to the conductor. It can keep track of everything. We can visualize these states in a lot of different ways. We can export this data into different measurement systems. So if you are like a Grafana house, you want to put it in your elk stack or whatever, you can do that. And then you can keep that data and build dashboards however you need to build those things, and however that fits your business case. Also you can use SNMP and streaming telemetry to monitor the health of the devices themselves. So this is kind of what it looks like. So this was one of my test routers. It has 2 physical connections. It has a broadband connection. In this case, it's DSL, and it also has that LTE connection. So each of these 2 connections has peerings to 2 aggregation routers. So it would measure each of those 4 peerings independently, and it'll tell you latency. Actually, I'll go to the next slide because I kind of split it and blew it up. It'll tell you, how much latency is across each of those paths, jitter and loss, and then again, that mean opinion score. If you can even say, oh, there's, 15 layer 3 hops on this link. If that number exceeds 20 for some reason, like there's some kind of internet disruption, and if that number exceeds 20, I don't want to use that link, that pairing anymore. So there's lots of different ways we can slice the performance of the network. And again, we can graph it out. So latency and loss, or latency and jitter at the top, packet loss at the bottom. This obviously is what you would consider not a healthy link. This was a DSL provider. So it's a relatively low bandwidth connection, but there is also a bit of loss on there. And so you can go to that provider and say, hey, I'm seeing this problem. And so just like you could with, a Zayo or whoever, I'm seeing this problem. We need to figure out what the problem is here. And then this is the LTE connection from that same site. So at this site, it was using that LTE link because there was too much loss on the broadband link. until we could get that issue resolved. So I wanted to kind of dive back into the IPsec versus SVR idea. So I'll step through this as in detailed as can. And I don't know if you guys can see, oops. I don't know if you guys can see my mouse.
I see it, yeah.
Okay. So you have a customer at a SD-WAN surf site, and they want to get to a web server that is, somewhere else in the network in the core. So the customer computer will send a packet. It says, I want to get to this web server, port 443. The kind of what a normal IP packet would look like. Source address, source port, destination address, destination port. It's a TCP IP packet. So the normal 5-tuple. So the packet gets to the SD-WAN router. In a regular IPsec SD-WAN, what would happen is that packet is preserved, but it gets encapsulated into an IPsec tunnel packet. So it'll say, well, my public IP address is this 97 address, and I need to get it to, the other end of the tunnel, which is this other public address, this 140 address. So I'm going to build a new IPsec header with a new 5-tuple. I have a bunch of other stuff I need to do, authentication headers, other IPsec stuff. I'm going to take that packet, the original packet, I'm going to encrypt it, and then I'm going to shove this all out onto the internet. And say in the case this is that DSL connection. I'm going to shove it out onto the internet. That IPsec tunnel will make its way across the internet. We'll unencapsulate it and unencrypt it on the other side. And then when it gets here, it looks like it did when it left the original, when it left the sender, and then it'll do its thing. So the issue is that process can lead to 30 or even 50% overhead. That it's a lot of data to have to add to each packet, and have to that when you're always encrypting the payload again, that extends the size of that message, depending on your encryption algorithms. So with SVR, what we can say is, that original packet arrives at the router, and we know we need to get it across, this public IP network, the internet network. So, and obviously, the internet's not going to be able to deal with these internal addresses. But instead of encapsulating it, basically what we're going to do is a network address translation scheme. If you were like at home, and your home computers have these 192.168 addresses, and you send these packets out, they get to your broadband router, and then so your broadband router would say, well, I'm gonna change the source address before I send it on the internet to whatever the provider's public address is. It's the same idea, except we're going to do it for both the source and the destination. So we know what the other end of the peering is, this 140 address, and we know what our local public address is. So basically all we're going to do is we're going to swap out the source and destination address, we're going to swap out the source to destination port so we can keep track of this flow later. And then we're just going to tell the other side what we're doing. We're going to say, this is our scheme for this particular flow. So when it gets those packets, it can undo it. And the result is the same. When the packet pops out on the core side of the network, it again looks the same as what it did when it left the original sender. But what we do is we save all of that overhead, both in terms of bandwidth and computation for encryption. So all that in mind, I'm going to shift gears and I'm going to talk about IMET for those of you who are not familiar with that program. IMET stands for Incident Meteorology. It's a nationwide National Weather Service program. The idea is whenever there's a big wildfire, a meteorologist would get deployed at Fire Command. So they can do localized forecasts. Sometimes they'll launch a weather balloon on site or have other sensors on site to collect specific data for that location. And then they can go to the fire commanders and say, based on my forecast, I expect the wind to change tomorrow to be out of the south at, 20 miles an hour. And so fire command can say, well, based on that, I can deploy my resources in a particular way, or based on, that, we'll have high winds tomorrow. We can't count on, tanker support. So we have to do something different. So the ability to get this specific weather information to these fire commanders very quickly is critical for them in order to be able to attack that wildfire. So this can happen both during actual, wildfires or during controlled burns or prescribed burns. For the IMET themselves, this of course means that they have to have reliable access to their tools. So they use a wide variety of tools located in lots of different places. When we were originally having these discussions, the IMET let me know, it's like, well, when I normally do this, I just do a hotspot on my phone. And if I am in a location where I don't have cell service, then I drive into town and go to Starbucks. And, on a personal note, before I joined NWave, I've been involved in the research and education community for a long time. And one of my, kind of guiding principles is I don't want scientists to have to be IT experts. And so I don't like, if someone is working on curing cancer, I want them to spend their time doing that and not spend their time trying to figure out why they can't copy their data from one place to another. And the same is true here. I don't want, these meteorologists to have to puzzle out, well, how am I going to get internet access this time? So I wanted to come up with a way to make it, kind of a no-brainer for them. And again, we're a federal agency, so we have these considerations like trusted internet. And these sorts of security constraints. And I don't want to have them leave site and go to Starbucks when they can't get cell. So this is kind of my back of the napkin sketch. I have considered making a prettier diagram. But I kind of like the nostalgia of, this was like the idea, let's get it down on paper. So we were working with uh, National Weather Service Western Region in general, and then the Boulder Weather Forecast Office specifically. So each WFO will have an incident meteorologist for that office. Even though it's a national program, the WFOs are kind of control that locally. So we know we're going to go to out in the woods. We don't know if we're going to have 5G or LTE. So, the non-terrestrial route kind of seems like the no-brainer. Starlink is, kind of where it's at right now. And so what can we do with Starlink? So the meteorologists will have, they'll take their laptop off their desk, they'll stuff it in their laptop bag, they'll grab their other gear and they'll go. So, or they'll be using a phone or a tablet. So we need Wi-Fi because we're not gonna, we don't want to have to make them figure out how am I gonna plug my laptop into somewhere. We already have, Enwave already has an enterprise wireless service. The For those of you who aren't familiar with like wireless as a service, generally what happens is you will deploy a bunch of access points. All the access points will contact a controller. User's traffic gets tunneled back over that controller, or back to that controller, and then that's kind of the point where they get network access. And so there's two modes that an access point can be in. It can be in tunneled mode, or layer 2 mode rather, or what's called RAP, which is remote access point. And remote access point means, it'll use whatever IP network it can. It'll make a tunnel back to the controller, and then you're good. And then you might say, well, wait a minute. If a RAP can do this tunnel junk on their own, why go through all this SD-WAN trouble? And I'll get to that in a minute. But we're going to be in a low power environment. And then again, we want to provide a minimal burden for the meteorologist, but provide a maximum amount of connectivity. So in April of this year, there was a scheduled burn in a place called Forsyth Canyon. So I thought, well, I'll take this idea. So this Starlink dish, the little SSR 130, I'll grab one of our regular N-Wave APs, and we'll go out and we'll see what we can get to work. So, build a layer 2 service across our overlay back to our wireless controller in Boulder. So you have Boulder kind of on the right-hand side of our map. The blue circle is the David Scraggs Research Center, DSRC, which is the main office building for NOAA in Boulder. It's on the NIST campus, kind of on the south side of Boulder. It's also where the Boulder WFO is located. And then the star up here is Forsyth Canyon. So, it's at the end of some forest road up in the hills. So it's 45 minutes, an hour drive to get there. And again, if you're, the meteorologist is up in the woods, this is my phone. I took this on my phone um, on location. I didn't have cell service. The nearest cell tower was 6 kilometers away, and it wasn't my carrier anyway, so I had nothing as far as data. Um, so I had the emergency only thing pop up. Um, and again, so the meteorologist had told me, it's like, well, if I don't have LTE, I drive back into town. It's like that, it's a 2 hour round trip. That's ridiculous. Um, so the basically I could lay the equipment I need out in the trunk of my car.
Andrew, we can't hear you.
Yeah.
Oh. When
Yeah,
did
ready
when
to
did you
go.
stop hearing me?
I hear you, Andrew. Is it, how about anybody else on the call? Thumbs up.
I hear him as well.
Okay,
Yeah, I can hear him too.
I can hear
Loud and clear here in New York.
awesome. Thank you. Maybe just a little glitch there. Thanks.
Um, so I drove up there. I had the equipment in the trunk of my car. And so that's me standing on this rock. So the fire command was deployed at a trailhead. Our original plan was we would have one of those cigarette lighter car inverter things, and we would power everything off that. To be honest, I forgot it. But luckily, the Forest Service had a little generator on site, so we actually wound up using that for power. So I plopped down the Starlink terminal just kind of in the middle of the parking lot there. The terminal, I don't know if I made a slide on this or not. We had selected the Starlink high performance flat antenna. Since then, Starlink has come out with a couple of other different products, like their mini antenna and such. But at the time, this was the antenna we had chosen. It's not small, which is not great, but what we were kind of trying to balance that the portability versus performance issue. So there's the meteorologist. His name was Bruno, is Bruno. So he had the laptop on the hood of his car. And again, I had most of the stuff in the trunk of my car. So I had our regular Aruba access point, the power supply for the Starlink dish, the SSR router with LTE antennas attached, which again didn't do me any good because I didn't have service, and neither did the router, and then the dish itself. And this might seem anticlimactic, but it just worked. One of the goals, again, one of the goals is to make things as seamless as possible for the user, for the meteorologist. So, when he's at his office, when he's sitting at his desk with his laptop, and he connects to the building Wi-Fi, he's familiar with that process. And it's a secure authenticated process. So from a networking perspective, we know who this person is. So if you wanted to go down the route of like zero trust network access and those more robust SD-WAN concepts, you can build those into these systems too. So the router itself, it powered on. The Starlink, got an IP address from the Starlink dish. It automatically established all the peerings it needed to, built the overlay network, and it was great. It took from, plugging stuff in, plugging stuff in to powering on to getting connectivity was about 8 minutes. So it was a very rapid process. We didn't have to stand around and wait for things to sync up or whatever. It all boots up and happens very quickly. The AP again is in layer 2 mode. It connected to the controller back in at the office, and the meteorologist saw exactly what he sees when he's sitting at his desk. He gets the same IP address as if he were sitting at his desk. He gets access to the same network services and the same connectivity experience. And again, power is important. So the dish itself, so I actually did 2 different tests when I was there, just as a comparison. Starlink ships with its own router, its own Wi-Fi router. So just kind of on a lark, let's see how things work with just that. So just the Starlink dish and its regular router is 90 watts of draw, which is very, very low. So if we swap out the Starlink router, put in our router, and add the access point, we're only up to 110 or 120 watts. And again, this is something that you can do on a very small, even car inverter. We wound up not going that route. Just in this, for the sake of transparency, that's not what we did, but that's we could have just left the car running and plugged it into the car for power. Performance itself was very good. We got about 100 through the SD-WAN service. We got about 150 meg a second. And again, from a user experience, he had everything just like he was at his desk. The way that this was deployed was purposefully almost a worst case scenario. So the idea when you're when I did the IPsec versus SVR walkthrough, that only applies to layer 3 services. Layer 2 services are still getting encapsulated because you need, when you're running a layer 2, like a VPN, a layer 2 VPN service, you don't know what all your protocols are going to be. So basically you just tunnel all that. It's like, okay, we're going to tunnel this VLAN, basically. And then the access point is also going to tunnel the traffic. So you're tunneling a tunnel and encrypting it to boot. So despite all that, essentially not taking advantage of a big aspect of this technology, we still get really good throughput. So, and again, if we're gonna hamstring ourselves, and I see the question in the chat, and I'll get to that in a second. If we're gonna hamstring ourselves, why don't we just put a rat in and let the AP do the tunnel and it'll be fine? So part of it is the flexibility of the transport. So one of the things that the IMETs told us is that if they're deploying for a like an actual wildfire, their connectivity will change over time. So they could roll up to a site and they might have decent LTE to start with. And maybe as more first responders get to the site, maybe that LTE gets congested. So like for the first hour, maybe you can use LTE, but as that degrades, like because in a disaster scenario, everyone is trying to get on the cell cell network. You can add your Starlink to the mix, and then as you're on site, as days pass, maybe Comcast rolls in and delivers some kind of broadband. So you can take that broadband and then you can plug it in and you can establish new pairings on your overlay, and the meteorologists don't have to do anything because the service they're getting is not changing. It's just the transport side that's changing. So we can improve the transport, and it can be seamless to the user. And again, we can get that visibility into how the network's performing. And if we decide, oh, we're going to deploy a server and we need to plug in an Ethernet connection, we can do that too. We can say, oh, you can get access to some other service through wired Ethernet. And so like for as far as like backup internet, as to the question in chat, there's a couple of different ways you can look at it. You can, like, if you have this at your house, and you have your normal broadband connection, if that were to fail, then the service could switch over to, if you have LTE and SIM card in the router, it'll just switch to that. And your connectivity would stay up and it would stay the same. So kind of the inverse of what I just walked through. Yeah. And it looks like I'm out of time, so I will leave it. Sorry, Rob, I ran a little longer than probably wanted me to.
No, all good. And I apologize as well. I have a hard stop right at the top of the hour. I have to jump over to the Federal IPv6 Task Force. I think there was a question about feasibility of, as a backup internet. I mean, in our use cases, Starlink anyway has been working really well from connectivity standpoint, bandwidth standpoint. So yeah, sorry we couldn't get as many questions here. Please feel free to reach out to myself, the ACT-IAC team, and we could provide some more information there. I will, in closing, say that the IMET use case really illustrated the mobility aspect of this and the mobility aspect of leveraging non-terrestrial networks, how fast it was to set it up. Andrew talked about the power draw, all that, and there's just more and more use cases that we could think of, especially on with the National Weather Service within NOAA, response type of activity, looking at hurricanes that just came through, or augmenting facilities that have really good connectivity, but in our case, we had a facility in Asheville, North Carolina that had really high available fiber service for the past 12 years, never have lost that site. This last hurricane we did. So a SD-WAN leveraging a Starlink or non-terrestrial, in this case, Starlink would be good because we did lose a lot of cellular in the area. It's a complement to our federal organization. So anyway, with that, sorry to run, going to close out. Thank you so much. Please join us November 7th for the next iteration of this. We're going to have a panel. We're going to talk to all of those folks that did the projects with us and keep the discussion going. So thank you very much, and we'll see you next time. Take it easy.